Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you're in the right spot, so go ahead and click the subscribe button. That said, let's get into the current video. In this video, I want to talk about a mixture problem that you would see in your introductory differential equations course. These usually are in this following format where you have a tank holding either pure water or water with some sort of a chemical mixed into it, and then I'm pumping water in, draining water out. And the idea is I want to model how much of that chemical is in the tank for at any point in time. So let me go ahead and run through the setup for this one. We have a tank initially containing 40 pounds of salt dissolved in 600 pounds of water. Then water with a half pound of salt per gallon is poured in at a rate of 4 gallons per minute. And the well-mixed solution, so again, what I'm assuming is within this tank, we've got these blades that are just, mixing it very thoroughly, very quickly. The well-mixed solution is drained at the same rate. Solve for the quantity of salt in the tank at any given time. Okay, so let's kind of set up our problem here. So solution. First and foremost, I'm going to say let's let Q of t equal the quantity of salt at time t. Okay, and then, well, what do we know? So a tank initially contains 40 pounds of salt. So right away that tells me that Q of 0 is 40. And I'm going to leave off units here, but Q of 0 is 40 pounds. And then we've got a rate of the water that's being poured in. We've got rate of water that's draining away. So ultimately what I have is this tank which has a water in it with salt dissolved. And what we're doing is we are pouring in water at a certain rate. Okay, and then we are also draining water at the same rate. Okay, and we want to again model how much salt is in this tank for any time. Now, there's multiple rates that are going on here. We have the rate that we are putting salt into the tank. We have the rate that salt is coming out of the tank. So let's talk about each of those. The rate salt enters the tank. Okay. Well, what do we know about that? So water with half pound of salt per gallon is poured in at a rate of 4 gallons per minute. So I don't know how many pounds per minute of salt is coming in. So what do we have? A half pound of salt per gallon is poured in at a rate of 4 gallons per minute. So I've got 1/2, and that is pounds per gallon. And that's being multiplied by 4 gallons per minute. And so what that gives me is 1/2 times 4 is 2. The gallons, those units cancel. So I get 2 pounds per minute of salt is being poured into this tank. But we also have water that's draining out. So what is the rate where the salt leaves the tank? Now, if I look back at the rate that the salt enters, it's a concentration times the rate of the water that's coming out. So what I need is the same thing. a concentration times the rate that water is leaving the tank. Well, what's the concentration of this salt that's well mixed? Well, it's going to be the overall quantity of salt that's in the tank at that time divided by how big the tank is. So in other words, that would be Q of T divided by 600 pounds per gallon multiplied by the rate that it's leaving the tank, which is 4 gallons per minute. And 4 over 600 would be 150. So this is 1 over 150, and that's going to be pounds per minute. Okay, so this gives me the rate that the salt enters the tank and then the rate that the salt leaves the tank. Okay, now what I want to do is I want to set up a differential equation for Q. So let me see, what do I have here that I still need? I think I might have everything here. We've got Q of 0 is 40. We've got all those different rates. I think I can erase all this with no problem. Okay, now let's talk about the rate of change of quantity of salt in the tank. The rate of change of the quantity of salt. Well, first of all, let's think of it this way. If the rate that the salt entered the tank and the rate that it left the tank was exactly the same, so in other words, basically I'm just pouring in the same solution that's in the tank, the same ratio that's in the tank that's already there, then the rate of change is 0, right? Because it's staying the amount is staying the same. So the rate of change of the quantity of salt in the tank is the difference of these two rates. It's the rate salt enters minus the rate that the salt leaves. That gives me a differential equation for Q. dQ dt is equal to, so the rate that it enters the tank was 2 pounds per minute. I'm just going to leave off units just to make it look a little cleaner. And then, oh, I forgot the Q down here, didn't I? So that should be Q over 150. Okay, so this is 2 minus Q over 150. So this is a differential equation for Q, which we can then go ahead and solve, along with the fact that Q of 0 is 40. So that would be my initial condition, which will allow me to solve for the constant of integration. Now, to solve this differential equation, I'm assuming that at this point, if you're watching this video, you've probably gone through a couple of techniques for solving differential equations, primarily using an integrating factor. So let's use an integrating factor on this. Add Q over 150 to the other side. I get dQ dt plus Q over 150 is equal to 2. Now remember that the integrating factor is given by e to the integral of the coefficient of the unknown function dt. And of course, the antiderivative of just that constant is that constant times t. So my integrating factor is e to the t over 150. Okay, so there's my integrating factor. And the idea is I take that integrating factor and I multiply it through the entire equation. So that gives me the following. E to the t over 150 dq dt plus e to the t over 150 q over 150 equals 2e to the t over 150, right? I simply multiply the entire differential equation by the integrating factor. And what happens is the left-hand side, again, just reminding you of how an integrating factor works, the left-hand side becomes the result of a product rule. And what I differentiated was the product of the integrating factor and the unknown function. meaning the left-hand side reduces to the derivative of e to the t over 150 times q, and the other side, again, is 2e to the t over 150. Okay. Now let's go ahead and solve for q. I have to undo the derivative operation, so I take an antiderivative of both sides. I get the expression inside the brackets is equal to the integral of 2e to the t over 150. So that gives me the following. Okay. Antiderivative of 2e to the t over 150 would be 300 e to the t over 150 plus a constant of integration. And then what I do, of course, is divide by this integrating factor to isolate q. So just to emphasize, q of t is equal to, so for this first factor, the exponential cancels, giving me 300 plus c e to the negative t over 150. And this right here is the function that gives me the quantity of salt in the tank for all time. Of course, I've got that constant of integration that we have to figure out what the value would be, and I can do that by using my initial condition. That 40 was the initial quantity of salt, and so the 40 is equal to q of 0. But on the other hand, q of 0 is 300 plus c e to the, well, negative 0 over 150 is 0. E to the 0 is 1. C times 1 is c. So to solve for c, I just subtract 300, and I get c is negative 260. Therefore, the quantity of salt for any time is the following. Q of t is equal to 300 minus 260 e to the negative t over 150. So this is the function that represents the quantity of salt in the tank. Now, I didn't ask this in the very beginning, but one just really quick observation we can make is if I take the limit of this as t goes to infinity, notice the exponential just goes off to 0, and so the quantity of salt in the tank will eventually be 300 pounds using, the fact that we're pumping in 2 pounds per minute. If we change that rate, so we change that concentration, then that would certainly alter, the terminal amount. But this would be the amount that we would eventually have in there. And again, the quantity, the volume of the tank was what, 600. So that means that the concentration would eventually be 300 pounds over 600 gallons. So in other words, half a pound per gallon. At any rate, thank you for watching. Please consider subscribing.